It's good to see everyone back. We're going to start Unit 3 with spacecraft and launch vehicles, so we'll be getting into some very exciting material. Up to this point, we've determined why space is important in our lives, and we've looked at orbits and trajectories. Now we're going to step back and look at the big picture of space mission design. As we've said before, this chapter lays the groundwork for more detailed material. You may not be building a spacecraft in your garage when we're done with this unit, but you'll understand some of the complexities of an actual space mission. In this lesson, we'll discuss space mission design. The idea is to design, build, and operate a fully functional spacecraft like the one we see here. We'll discover how designers use the tried-and-true systems engineering process to convert user needs into complete space missions. We'll learn how these needs form the basis for the mission requirements and constraints from which we decide how all elements of a mission will fit together. From these top-level requirements, we'll learn how to design the payload and subsystems that make up the spacecraft. And we'll discover that the payload is one of the most important drivers of any mission. We have some great examples to explain the concepts presented here, so let's get started. If you've ever built a doghouse or been on a school committee to plan an activity for your friends, you've probably used a systematic approach to turn your needs or requirements into a final product. We're going to look closely at this process to see how we can apply it to designing anything from a backyard barbecue platform to an orbital observation platform. We'll start by looking at the process's basic steps and then apply them to space mission designs. As NASA created the International Space Station shown here, the design depended on careful space systems engineering. A well-defined process has been developed over the years, and this process starts with the mission requirements. We just spoke about the systems engineering process, and we'll get to that in a minute. But first, let's define systems engineering. We know that all design problems begin with a need or requirement. For example, when NASA was mandated by President Kennedy to send astronauts to the moon, they designed the Saturn V launch vehicle shown here. Over time, engineers have developed a well-tested process for translating stated needs into complex systems. This process is called systems engineering. A simple example of how you can use systems engineering is the problem of designing and building a deck, like this one. You'd start with a general statement of your basic requirements. For example, you would need a flat, dry area in your backyard that's roomy enough to house your barbecue and entertain your friends. You probably want an easily maintained deck that has protective railings so people wouldn't fall off. Getting the basic requirements together is a key first step in the systems engineering process. Along with these general requirements, you'd probably define some real-life constraints or conditions. You might specify that your deck should cost under $10,000 to build, so you have a budget in mind. You could assign a timeline for the project so your deck was completed by the early summer, and tasks would be scheduled in some order to assure the deck is complete. You could make sure that your deck was constructed in such a way that it would last as long as the house you live in. This would suggest that quality must be high and that all materials and construction techniques are done in a reliable fashion. Remember in the last section we spoke about the trade-offs between deceleration, heat, and accuracy for the spacecraft reentry mission. Well, the systems engineering process has trade-offs too. For the deck project, we have to make decisions based on the trade-offs between what you can afford when you need it and what you really want. Once those decisions are made, you can narrow your focus and start to specify the deck's characteristics, such as size, shape, materials, and so forth. We're going to stick with our deck building project, but start to think in terms of a space mission while we go over the systems engineering process shown in the diagram. Now that we've defined the requirements and constraints of our deck project, we can get down to the business of designing what it will look like and how to build it. We'll need to make some detailed drawings, specify the amount and type of lumber, choose the types of nails and bolts, as well as state all the other construction details. Next, you'll need some design tools to help you with calculations and other tasks. And finally, After you've gathered all the requirements and done the design, you'll need to look everything over to make sure that your design truly meets your needs. In this diagram, there are 3 loops that describe the process. The requirements loop that connects top-level mission requirements and constraints with system requirements and constraints. The design loop that ties together system and subsystem requirements, and finally, the validation loop, which helps answer the question, am I building the right system? You should have a solid foundation for the systems engineering process by following this diagram. It would be a good idea to go back to the diagram during this section so you're positive you understand the process. You might even try to draw it from memory while you go through the steps. Yogi Berra, the famous baseball player, coach, and manager, who was also a master of stating the obvious, once said, "If you don't know where you're going, you'll probably end up someplace else." It turns out that not only was Yogi right, but his logic can be applied to defining mission requirements and constraints. From our last slide, we know that in order to begin the systems engineering process, we have to define top-level mission requirements and constraints. These requirements tell us, and others, the basic needs for the mission. We've got to ask the questions, what end result do we want to achieve? What is our ultimate objective? And in space terms, what is the mission? You've seen this emblem in earlier sections, and you'll remember that it defined the space mission architecture. Here we're going to focus on the centerpiece called the space mission, which is described in the mission statement. In order to define a space mission's requirement, we have to begin with a mission statement that clearly and simply lays out 3 important points. First, the mission objective explains why we are doing the mission. Second, the mission users are the people who will benefit from and use the information. And third, the operations concept says how all the mission elements will work together to do the mission. For this first systems engineering step, we'll focus on the heart of the mission architecture to decide on our mission's form and how its elements will interact. The architecture we define, including the necessary systems and subsystems, must ultimately satisfy our mission need. Okay, that's a lot of information to digest. So let's look at an example. We just said that in order to define a space mission's requirements, we should start with the mission objective or the mission need. We'll begin with the integrated FireSat example and continue with it throughout this lesson and some future lessons. We are all concerned with detecting forest fires and know that every year forest fires destroy tens of thousands of acres of valuable timber, wilderness resources, and animal habitats. But we're talking about space. So how do space assets help us track and put out the fires faster? Think about some of the ways we use information, some of which you've already learned in this course. Any ideas? You'd be right if you said cable TV, worldwide weather reporting, global positioning system or GPS, and strategic systems. So now, let's get down to the specifics. The material in this section is so important to later sections that we'll repeat some of the concepts to make sure you understand them. Be patient, follow along, and above all, take the responsibility to make certain you understand it. Let's look at the diagram while we review the mission statement. We've got to identify the mission objective, which is why we do the mission. For FireSat, we want to detect and locate forest fires worldwide and provide timely notification to the users. Then we need to name the users, the people who benefit from and use the information. That one's easy. The U.S. Forest Service and other national and international agencies that are responsible for fighting fires would be the primary users. And finally, we need to identify the operations concept, which explains how the mission elements fit together. In this case, several concepts are possible. So let's pick a concept that relies on a number of spacecraft in low Earth orbit to detect and locate the fires. Here you see FireSat-1 and FireSat-2 in the diagram. Once the FireSat satellites detect and locate the fires, the system will communicate this information through the internet, and the entire mission will be controlled using a single dedicated ground station. So far, we've mainly focused on what we want FireSat to do. But mission constraints are equally important. Remember in our deck example, our constraints were budget, schedule, and quality. Our FireSat mission and all other space missions typically have the same three constraints. Let's take a look at the diagram. I'm guessing all of you are on a budget that you have to keep close control over. Well, the bottom line program cost is an easily recognized constraint to anyone who operates on a budget. Next, you know you must arrive at class and have your assignments done on time according to a schedule. Most space missions are the same because they may have to meet a launch window or simply ensure the required spacecraft is on station in time to serve the paying customers. The last constraint is that you do whatever it takes to make certain all the pieces of your life come together to meet the goals you set for yourself. Similarly, systems engineers must design a spacecraft containing subsystems that work together reliably to accomplish the mission. An example of performance for a FireSat is the size of fire it can detect. Our users may want to be able to detect a small campfire, but if the spacecraft can only detect raging fires, we will have a performance problem. So, we have to make sure our proposed system meets the user's needed performance. Mission requirements center on the big picture items which are the reasons for and results of the project. Systems requirements focus on the system architecture's elements to describe in more detail what we expect of each element for mission success. Typically, the least constrained space mission element is the spacecraft. We usually divide the spacecraft into two parts, the payload and the spacecraft bus. The payload consists of the sensors or other instruments that carry out the mission. For example, if we're looking for forest fires, the payload might be a camera or heat detector. And the spacecraft bus is a collection of subsystems that support the payload. Keep this information about the payload and the spacecraft bus in mind. We'll talk more about it in a moment. Payload requirements usually have the most influence on the spacecraft's design. We define the mission's subject to be a natural or manufactured object or phenomenon that the payload will sense or interact with. We characterize the subject by such things as its color, size, shape, temperature, chemical composition, or frequency. Only after we know the subject can we lay out clear, simple payload requirements. Take a minute to think about examples of natural or manufactured objects or phenomena that a payload could sense and interact with. For example, if we are looking for F-16 aircraft that are the subject of our mission, we might use a camera to search for airplanes that look like F-16s. We could characterize the F-16 subject by a certain wingspan or by how its nose or tail looks. Okay, let's go back to our FireSat example. The obvious subject for this mission is forest fires, and the mission objective states we should detect and locate forest fires. That sounds good, but there are other questions we should be asking ourselves in order to help the designers focus on the payload. Can you think of some questions we need to ask and answer? How about what kind of forest fires there are and how big or hot do they get? And what characteristics of forest fires, such as light or smoke, should the payload detect? These questions are important to the payload designer because we don't want to send out an alert when someone starts a campfire that's under control. But we also don't want to ignore a multi-acre blaze that may be out of control. Once we know these payload requirements, the rest of the mission elements fall into place. For instance, the type of payload greatly determines the mission orbit. The payload's mass, volume, power, and other requirements will determine the spacecraft's basic size and mass. We use the requirements loop to reevaluate the requirements based on new information. We saw this diagram earlier, but now we can see where the requirements loop fits into the overall systems engineering process. The payload establishes spin-off requirements for the spacecraft bus. We defined the spacecraft bus earlier as a collection of subsystems that support the payload. These spin-off requirements are where and how precisely the spacecraft must point, the amount of data that must be processed and transmitted, how much electrical power the payload needs, the acceptable range of operating temperatures, as well as the payload's volume and mass. In the next slides, we're going to bring all this information together. Throughout this course, we've had some awesome examples to help us with complicated information. Well, now we're going to look at one that I really like. We're going to discuss how systems engineers go about designing the payload and the spacecraft bus. Follow along with the diagram. Here we have a plain old school bus we can use to demonstrate the relationship between the spacecraft bus and payload. Of course, the students are the payload for the school bus, and the school bus must provide all necessary functions to care for the students and get them to school. The horn, radio, and driver communicate between the students, other vehicles, and the community. The steering wheel and associated systems give the bus vehicle control. The battery and alternator supply electrical power. The radiator, air conditioner, and heater make available a suitable temperature environment for the bus and students. The engine and drivetrain deliver propulsion, and finally, the body and frame provide the overall structure and mechanisms that keep things together. The school bus brings everything together that's necessary to do the mission, which is to get students to and from school. Let's look at the bus again and figure out what we need to know so we can design the bus. In designing a school bus, we need to know how far and how fast the students need to go, so we'd make certain the bus had a big enough engine and a large enough gas tank. We'd also have to make sure the bus was large enough to carry all the students. Since the students are the primary payload, we'd have to be positive they were comfortable by making sure they didn't freeze or get too hot. Then finally, we'd have other requirements that support the mission of getting students to and from school. Okay, let's look now at the Magellan spacecraft, which successfully mapped over 98% of Venus's surface. This is called an exploded view of the spacecraft, and the term makes many designers cringe because the last thing they want to happen to their spacecraft is to have it explode. The payload is shown on the upper left side of the diagram and consists of several instruments, like an altimeter that helps figure out how high some of the terrain is on Venus. The Magellan spacecraft bus has a large high-gain antenna, as well as smaller medium and low-gain antennas for communications and data handling. Many different structures like equipment modules, thrusters, tanks, and adapters are used to keep different parts of the spacecraft in place. The solar arrays provide power. A star scanner is used to determine where the spacecraft is pointed. So you can see that the spacecraft bus is similar to the school bus in that it provides for the care and feeding of the payload. Now, let's look at some details. School bus drivers must know what route to take, where they are, and how to steer their buses to get where they need to go. These requirements are all part of controlling their vehicles. On the spacecraft, a similar subsystem steers the vehicle to control its attitude and orbit. Basically, there is nothing worse than a spacecraft with a bad attitude. On spacecraft, the subsystem that steers the vehicle is the attitude and orbit control subsystem. The Tracking and Data Relay Spacecraft, or TDRS, relies on its attitude and orbit control subsystem to keep it pointed in the right direction and allow it to communicate with ground systems and other orbiting spacecraft. We can easily identify the driver on the school bus. It's the person in front, behind the steering wheel. On a spacecraft, the driver is less easy to pick out, but its role is just as important. The driver of the spacecraft bus is called the Communication and Data Handling Subsystem, or CDHS. The CDHS collects and processes data from on board the spacecraft and from the ground. It often decides on courses of action and executes commands. Here, a NASA astronaut talks to mission control while analyzing mission data. Just like the school bus, spacecraft depend on electrical power to keep many of its components running. The electrical power on a spacecraft is no different from that used to operate your television or stereo. Unfortunately, in space, there's no outlet to plug into, and an extension cord to Earth would have to be very long. Therefore, a spacecraft must produce its own electrical power from some energy source, usually the sun. You can see solar panels extending out from the golden box-like structure on this European Space Agency spacecraft. People and electronics like to be at room temperature in order to operate properly. To keep the payload, the astronauts, and equipment healthy and happy, the Environmental Control and Life Support Subsystem, or ECLSS, must keep the temperature within an acceptable operating range. It must also provide such things as air, water, food, and other necessities. Here, astronaut Katie Coleman tends to a mouse ear plant on Columbia's flight deck. A school bus engine would overheat without a radiator to keep it cool. Similarly, a spacecraft must regulate the temperature of its components to keep them from getting too cold or too hot. People need an atmosphere in which they can breathe at a comfortable temperature. They also need humidity and pressure, along with food and water to stay alive. In addition, on the Space Shuttle and the International Space Station, something must protect astronauts from the harsh space environment. The spacecraft's ECLSS maintains the required temperature, atmosphere, and other conditions needed to keep the payload and astronauts safe and secure. A school bus's structure holds it together and must be sturdy enough to handle all the stresses while holding all other subsystems in place. Spacecraft structures must do the same thing while the spacecraft is launched and in orbit. Here we can see a technician working on one of Ball Aerospace's remote sensing instruments. You can see the structure that holds everything together and supports it during launch. Besides holding everything together, the spacecraft also has many parts that crank, extend, bend, and turn to deploy solar panels, extend antennas, or handle other functions. A school bus has an engine and drivetrain that supply torque to the wheels, moving the bus where the driver wants it to go. In space, we use rockets to expel mass in one direction, which causes the spacecraft to move in the other. Remember Newton and the concept of equal and opposite reaction? Large rockets on launch vehicles produce the thrust needed to get the spacecraft into orbit. Once there, smaller rockets in the spacecraft's propulsion subsystem produce thrust to maneuver it between orbits and control its attitude. Now, we'll go back to our spacecraft example. The spacecraft design process shows how a spacecraft's subsystems depend on each other. When we adjust the design of one subsystem, we're likely to have to adjust some or all of the others. Notice that all subsystems are somehow linked together. This diagram also shows that during the design phase of a mission, things are constantly changing as we learn more and more about each subsystem. One of the most important rules of engineering design is better is the enemy of good. We can over-design a perfectly good system while trying to reach for a better design. Think about this rule, because we'll ask you about it again in the activities section. To help make complex design decisions, mission planners and systems engineers have many design and analysis tools in their toolkit. These range from simple back-of-the-envelope calculations using a pencil, paper, and calculator or spreadsheet to complex computer simulations requiring hours of runtime. The final responsibility for the mission success or failure rests with the mission planners and developers. These people must do a reality check on all analysis results to make sure they make sense. The designers must understand the theories behind the analysis to assess whether or not the results are reasonable. So if the spacecraft breaks, we can't blame it on the computers. Too often, the people responsible for specific subsystems get so involved in designing their own small piece of the mission that they lose sight of how their decisions affect other subsystems and the mission's overall performance. This figure offers a humorous look at how subsystem designers often view the spacecraft. It shows all the subsystems we've talked about today. For example, rocket designers might create an awesome rocket, but pay little attention to the spacecraft payload and subsystems. Of course, we don't want subsystem managers to look at the spacecraft from just their point of view. To design a spacecraft to meet the objectives on time and within budget, everyone involved with a project must keep one eye clearly focused on the overall mission, which is the big picture we talked about at the beginning of the section. This diagram is a more complicated example of the one shown earlier. Make sure you understand how the added information enhances the original diagram. For the activity part of this section, I'd like you to do something a little different. There are 3 very important processes discussed here, and it's important that you understand them. So I'd like you to draw the systems engineering process shown on slide 8 from memory and then check to see how you did. Take a minute to think about examples of natural or manufactured objects or phenomena that a payload could sense and interact with. Share them with your class. Look at the diagram on slide 16 and talk about how the forest fire, a river, and a city might all factor into the FireSat mission. Suggest some other terrains that could hinder or aid in the FireSat mission and why it's important that the spacecraft is able to provide this information to the users. Explain why better is the enemy of good for engineering design. Come up with some examples of why this idea is true. It means we may over-design good systems in a mistaken search for something better. Refer to your text for some ideas. Well, we've had some very explicit examples which explain concepts that are rather complex. We've talked about how designers use the tried-and-true systems engineering processes to convert user needs into complete space missions. We've learned how these needs form the basis for the mission requirements and constraints that let us decide how all elements of a mission will fit together. From these top-level requirements, we've learned how to describe the payload and subsystems that make up the spacecraft. And we know that the payload is one of the most important drivers of any mission. In the next lesson, we'll look in more detail at space vehicle control systems by describing what they contain and how they work.